Okay, so let's get on with it. Today we're going to talk about the section 5.3, the method of least squares. Okay, and this is a fairly important method, and it's a nice application of two things that we've seen before: the direct sum and the fundamental subspaces theorem. Okay. Now, it's not just the direct sum, but one particular version of one particular fact that we mentioned last time, which was that if you have a subspace S in Rn, then you can split Rn into the direct sum of S and its orthogonal complement. Okay, right? Whenever you have a subspace in Rn, you can take its orthogonal complement, right? You can take its orthogonal complement and then decompose Rn into the direct sum of those two guys. Okay. Okay. So, and then the fundamental subspaces theorem, we're going to use the part that says that the range of a curve is the null space of A transpose. Okay, so those are the parts we're going to use. Okay. Okay, so here's the idea. Suppose we have an overdetermined system. AX equals B. Okay. AX equals B. So A is an n by n matrix. Good. You have a question?
Is that A transpose under fundamental subspace theorem?
Here.
Yeah.
A transpose, yes.
Also, what is the C notation with S?
This subset is a subset of, like you guys in this class are a subset of the set of all students in the world.
What's in between that one and the one that looks like an E?
Looks like a what?
An E?
Oh, that's element. So you, Mariah, are an element of the set of students in this class, but you are not a subset, right? You're not a set, right? If I say the set of Mariah, that's a subset of the set of students, right? So let's say the set of students is called S.
So it could be an element or a set.
Well, you are an element of this set. This set consists of one thing, you.
Yeah.
Right. So you, Mariah, are an element of this set. But I can also throw in other people available. Right. You are an element of that set. So a single element. This is a set that's included inside of another set.
Okay.
It's interesting. You guys don't learn set notation in junior high school anymore.
Or I forgot.
Yeah, maybe. Okay, so suppose we have an overdetermined system, right? So you have an m by n matrix where m is bigger than n, right? So the number of rows is bigger than the number of columns, right? Number of rows is bigger than the number of columns. In other words, you have more equations than unknowns, right? So more equations than unknowns. Okay. For example, right, you are in R2, and somebody says, I have these 3 lines, and I want you to find the solution set of the points that lie on all 3 lines, right? I want you to find all the points that lie on all 3 lines simultaneously, right? Well, there's no solution, right? There's no point that lies on all 3 lines unless you're really lucky, right? Right? Chances are that it's not going to happen. Okay. Chances are that there's no solution, right? So more equations than unknowns, there's likely no solution. Okay. There's likely no solution. Instead of trying to solve this problem, which is impossible, we change the problem. Okay. instead of trying to solve that, we say, right, so here we want x that satisfies this, right? But there is no x. There is no x. So we change the problem to, can we find x such that ax minus b is small? Well, what do we mean by small? We mean that its magnitude is small. Right? We are hoping that we could find an ax. We wanted to find an x so that the difference is 0. But there is no such x. So instead, we give up on that and we say, can we find an x such that ax minus b's magnitude is minimal? Right? Is the smallest possible. Right? There's nobody else smaller than that. There's no other x that gives you a smaller error than that. Yes, Sam?
I understand why we want to find like an intersect point, but if there isn't one, what's the benefit of finding a point that's minimal?
Well, you could, it's this is sort of like your best possibility. So, for example, this sort of stuff is the basis for the mathematics behind image cleanup. Like, that is, for example, I don't know if I've described this before, but you have a picture and somebody has typed all over it with Adobe Photoshop. Okay, you'd like to get rid of those letters. Okay, you'd like to get rid of those letters, but and there's a way of basically finding like the best. You don't know what actually lay under those letters, but there's a way of finding like the best guess for them, like in some sense the best guess for those letters, and it's actually really amazing. I wonder if I don't have my computer with me, but there's a way of basically making a guess of what lay under those letters and then removing it, and it's kind of astonishing what can be done. So it's an unsolvable problem, but you can find some answer that is kind of remarkably good. Okay, so yeah. Okay, so yeah, so you say, well, let's find some sort of best possible answer. Okay, so so that's the second form of the problem. Can we find x such that okay, so now we're going to rephrase that slightly. Okay. We want to minimize. Right. We're trying to minimize this ax minus b. So we say, can we find the element p in the range of A such that the magnitude of p minus b is minimal? So this is just a very tiny change in what we're saying, right? I mean, it's just a very tiny rephrasal. Right? We're looking for x such that ax minus b is minimal. We're looking for some p in the range of A, right? In other words, something p is going to be A of something, right? P is in the range of A. In other words, p is A of something, right? So we're looking for something in the range of A such that p minus b is minimal. Okay? It's almost exactly the same thing. Okay, not really a rephrasal at all. Okay, but this allows us to think a little bit differently. So notice. The range of A is a subspace, right? The range of A is a subspace, and so our goal then is to find a vector in a subspace whose distance from B is minimal. Right? So that's our sort of general goal, right? Right. We have some subspace S, say, and we have some vector B, and we want to find a vector in the subspace such that the distance to that external vector is minimal. Okay. Well, you can probably guess what it's going to look like, right? What do you think will be the vector in S that is closest to B? If I have, suppose we there's something like this. Here is S, and here is B. Right? And I say I'd like to find the vector in S that is closest to B. What do you think it's going to be, Eric?
Projection of the vector on the subspace?
You drop orthogonally down, right? And you say, okay, that's probably it, right? This guy here. Right. And so that actually turns out to be the right thing to do in all dimensions. So your three-dimensional intuition, in three-dimensional space with a two-dimensional plane, that's sort of the obvious thing to do. That actually works for all spaces, all Euclidean spaces and whatever dimensions you want. Okay. So I'm going to erase this. No, I'm going to leave it up. So here's the theorem. Let S be a subspace of Rn, and let B be some vector in Rn. Then, there exists a unique vector P in S for which the distance of P to B is minimized. In other words, if we take any other vector, if we take, given any vector y in S, the distance to y is greater than or equal to the distance to P. I don't know if maybe I don't even need to write that. You know what I mean. The distance is minimized. Part 2, P is that closest vector if and only if B minus P is in the orthogonal complement of S. Okay. In other words, the way that we find it here's our S, here is our B. The way we find it, we say the guy we're looking for is the one where if we subtract that off from B, then we get something perpendicular to S. Okay. If we subtract that thing off from B, we get something perpendicular to S. Okay, so that will be that, what we said about the three-dimensional case is going to be true in higher dimensions. Yes, sir?
Well, the theory hold also for P minus B, which is has to be
Hold for what?
it's B minus P in the orthogonal space. Could it be P minus B?
Sure, right? That's the same. I mean, that will just be the negative of that, right? So it'll be like this. Okay. Okay. Everybody getting the idea? I hope. Right? So this theorem says that if you have a subspace, and some vector outside of it, then there exists somebody in that subspace that's closest to this outside guy. Okay. And the way you get it is by looking for the vector so that the difference is orthogonal to the subspace. Looking the vector in the subspace where the difference is orthogonal to the subspace, right? So I don't want somebody like this, because then the difference is no longer orthogonal to the subspace, right? I want the guy where the difference is going to be perpendicular to the subspace itself. So why does that happen? Let's see how this works. And like I said, this basically hinges on the direct sum decomposition. So you're saying, well, S is a subspace of Rn, and S is a subspace. So we can decompose Rn into S direct sum as per. Okay, right? And so, you can probably tell what I'm going to do. What am I going to do? What am I going to do with B? I'm going to take that B, and then I'll direct sum, take its direct sum decomposition, right? I've got my B here, right? And then I will break it up into something parallel and something perpendicular. Yeah. What?
Can you explain the rest again?
So remember, we say W is U direct sum B. Okay, you have a subspace, and then you have a vector space, and then you've got two subspaces in it. Okay. We say this is true if every W in W can be written as W equals U plus B, where U is in U and B is in B, in a unique way. In a unique way.
What is unique way? What is a unique way?
In other words, there's no two ways to do it, right? If somebody gives you another expression, U prime plus V prime, well, those must be the same. The U's must be the same and the V's must be the same. Sort of like the standard example you want to keep in your mind is the XY plane and say the Z axis, right? Then you can express Rn as, let's call this thing U, call this thing B. You can express Rn. Everybody in Rn can be expressed as somebody in the XY plane, right? Everybody in Rn can be expressed as somebody in the XY plane plus somebody along the Z axis, right? And there's only one way to do that. So that's how you want to think about it. Okay, so let's remember where we are. We're trying to show that there is a closest guy to B. Okay, right? We have our subspace, we have our B, right? And we're trying to show that there's a closest guy in S to B. Okay, there's a closest guy. Okay, and so what we do is we say, okay, we have this direct sum, so let's split B up into those two parts. Right? What we're calling U and V up there. Right? You can split B up into something in S and something in S perp. Right? Because you have a direct sum. So I claim that this Bs is what we're looking for. Right? The vector in S with minimal distance to B. Okay, so why does that happen? Take any, why is that true? Well, take any vector V in S. Take any vector V in S. Okay, so right now we've taken our B and we've split it up into part in S and a part perpendicular to S. Okay, and what we're saying is that this guy here is our P, right? That's what we're hoping. This guy here is the P we're looking for. Okay, everybody all right? Ask questions. If stop me if I'm going too fast. Yeah, Mariah.
And so this is like right here. We're trying to answer the question of like why is BS and BS.
Why is BS the best one?
As opposed to like
somebody else. Like, how do we know that?
There's another way to form B. Or no, wait, there isn't. Why isn't there another way to form B? With the direct sum.
Because it's unique.
Because it's unique.
Yeah, we proved that last time.
Yes. Yes. So, I mean, that's by. Yeah, we proved. This is what we proved last time, right? That if you have a subspace, then anybody can be expressed as the direct sum. Then your ambient space can be expressed as the direct sum of that subspace and the orthogonal.
Okay. There's only one possible combination of S plus S curve for each.
Right. For each vector in your space, there's only one way to express it as somebody in S and somebody in S perp. Okay. So this BS and BS perp are the only ways you can express B as something in S and something orthogonal to S. Okay. So here we're trying to show that that this guy is actually the closest to B. Okay, the closest to B. So let's take some other vector V. Okay, let's take some other vector V that's in our subspace S, and we'll see that it's actually farther away. Okay, as you expect. Then, if you look at B minus B, the magnitude of B minus B squared, well, this is the same thing as B minus BS plus BS minus B squared. Okay. We do something funny. We throw in a 0. Okay. We subtract this thing and we add it back in. Okay, and now we say, well, where is this thing? B minus BS is in S perp, right? B minus BS is BS perp, right? So that's in S perp, right? Everybody okay? Right? BS minus V, where is that? Well, V was in S, and BS is in S, so the difference is in S, right? Right? Okay. Okay. So what we've done is we've expressed this thing as the sum of something in S perp and something in S. Okay, we've got these two vectors, something in S perp and something in S. Okay. So think, if I have two vectors and they're perpendicular to each other, right? I have something in S perp and I have something in S, right? And I'm looking at their sum, their vector sum, the magnitude squared of their vector sum, right? Well, what's that going to be? These guys are perpendicular to each other. It'll be magnitude of u squared plus magnitude of v squared, right, by the Pythagorean theorem. Okay. So by the Pythagorean theorem, and maybe you're kind of skeptical and like this. We are in Rn. Right? Do we have a Pythagorean theorem in Rn? You do. I'll leave it to you as a proof. It's easy. It's easy. Right? Here I can. No, it's easy. Right. No, let me just tell you. Okay, look. This thing is the dot product of this against this, right? Whoops, this against this. Right? But u and v are perpendicular to each other. Right? These guys are perpendicular to each other, so when you take u dot v and v dot u, that's 0. Right? And so you end up with the magnitude of u squared plus the magnitude of v squared. So that's it. Anyway, I'm going to erase it. So by the Pythagorean theorem, you get that this is equal to the magnitude of this squared plus the magnitude of this squared. Right? C squared equals A squared plus B squared for a right triangle. Okay. But that is bigger than or equal to the distance of b to bs squared. Right? And so you see that the distance of b to v is greater than or equal to the distance of b to bs. Right? And that they are equal if and only if bs minus b equals 0. Okay. Right? Let me say it in English. So if you take any vector in S, its distance to B is bigger than the distance of BS to B. In other words, BS is the closest guy. BS is the closest guy in S to B. Right? Because if we take anybody else, well, the distance is bigger than or equal to this distance. Right? If we take anybody else, right, the distance of that guy to B is bigger than the distance of BS to B. Okay. And the only way that they could be equal, right? The only way they could be equal is if the distance from BS to V is 0. In other words, when V is BS itself, right? I.e., V would have to be BS itself, right? It's going to be strictly bigger than this unless you actually have BS itself. Okay. And that basically gives it to us, right? We were trying to show that there's a unique guy whose distance to B is smallest, right? And that's what we said, right? We got here. We see that BS, the distance to B, is smaller than anybody else, right? That's what we got. And that occurs when B minus P is in S perp, right? And that's what we have, right? It occurs when P is, B minus BS is perpendicular to S. Any questions? Any questions? Right, so we're trying to show that this BS is the best, and we see that if you take anybody else, then you get a greater distance. Right, you get a greater distance. So BS is the best. Okay. Any questions? Anybody confused? Any questions? Yes. Okay. Let's go on. Okay, so what does this tell us? This tells us that yeah, great.
What would you think to put it? So by putting in minus BS plus BS into the B minus B squared,
How does one think to do that?
Yeah.
Well, I mean, it sort of makes sense because you're trying to compare this to the distance to BS, the distance of B to BS, right? And you're starting off with this thing B minus B. How do you work in the distance to BS? Well, you have to throw in BS somehow.
Yeah.
Right? So it's sort of that's right. You have some information, right? And you want to work that in. It's not that information seems irrelevant here until you introduce BS somehow.
Okay.
Right? So, yeah. It's okay. So again, we've rephrased the problem. Okay. Remember what our problem was? It was find P in the range of A such that B minus P is minimal. Right? That's what it was. And now we're saying that the problem is find X such that B minus AX, find X hat such that B minus AX hat is perpendicular to the range of A. Right? This is your P. Right? Find P such that B minus P is perpendicular to the range of A. Right? Thanks to our theorem, our problem is now this problem. Find an X hat such that B minus AX hat is perpendicular to the range, perpendicular to the subspace. Okay, but now we can, you know what we're going to do now. We've got the perp of range of A. That's the same thing as the null space of A transpose by the fundamental subspaces thing. Right? So we get find X hat such that A transpose B minus AX hat equals 0. Right? ID such that AT AX hat equals AT B. Yeah. Yeah, come here.
What's A hat again? Or
X hat.
Sorry.
X hat is what we're looking for.
What is that again?
I mean, if you want, I could just call it X, the vector X. But in the book, they use this notation X hat, so I'm going to use their notation. You're looking for a vector. Call it X hat. Okay. Okay, so what have we done? We've taken the impossible problem, right? Ax equals b. We want to find an x such that ax equals b. There is no such x. Okay. Instead, we change it to a problem that has an answer, right? Find x hat such that ATA x hat equals ATB. Okay. And when you solve this, then you get, then AX will be the closest thing to B that's possible. Okay. Now, once you get it, then AX is your best least squares solution. Okay, it's not a true solution, but it's your least square solution. Okay, this new set of equations is called the normal equation. Normal is another word for perpendicular. Okay, and okay, notice if ATA is invertible, then you can solve for x hat. Right? You can just solve for x hat by multiplying on both sides by the inverse. Is a solution, and then AX equals ATA inverse ATB is the projection of B onto the range of A. In that case, we call this thing projection operator. Okay? In that case, this is called the orthogonal projection. Onto the range of A. So you have this thing that just automatically projects onto the range of A. Now you give it something and it gives you the projection. Sorry, I'm kind of running out of time here, but let me do one quick example. So this is actually from your text. Find the quadratic formula, the quadratic equation, C0 plus C1x plus C2x squared. Find the polynomial P of x such that that best approximates, say this way, that has the best least squares fit to the data 0, 3, 1, 2, 2, 4, and 3, 4. Okay, so the picture is this. You have these 4 points, excuse me. You got 0, 3, 1, 2, 2, 4, and 3, 4. Okay. And somebody says, I'd like a parabola that passes through these 4 points. Okay. And you say, that's too many points, right? Because 3 points determine a parabola, but you've given me 4. Right, you've overdetermined. There's probably no parabola that works for this. Okay, so you say, okay, well, you can find the best, you can find the best possible answer in some sense. Right. So notice we want, right, P of 0 to be 3, P of 1 to be 2, P of 2 to be 4, P of 3 to be 4. Right? But P of 0 is C naught. P of 1 is C naught plus C1 plus C2. P of 2 is C naught plus 2C1 plus 4C2. Oops. 4C2. P of 3 is C naught plus 3C1 plus 9C2. Right? And so we have a linear system of equations. Right? We want, right? We want C naught, C1, C2, such that C naught, C1, C2 equals 3, 2, 4, 4 equals 1, 0, 0, 1, 1, 1, 1, 2, 4, 1, 3, 9. Yeah, Connor.
Where do you get 9C2 from?
9 because this is a 3. Right, so P of 3, that's C naught plus 3C1 plus 9C2. Like 3 times 3. Okay. So right here, so we can write our problem as this overdetermined linear system. We want C1, C naught, C1, C2 such that this happens. Of course, there's nothing, it doesn't work. There's no C naught, C1, C2 that works. So instead we change it to, we solve instead A transpose AC equals A transpose B. Right. We just multiply both sides by 1, 0, 0, 1, 1, 1, 1, 2, 4, 1, 3, 9. Right. Okay, so you get the normal equations. Right. We instead solve the normal equation. And it turns out that this has a solution. You get P of x is 2.75 minus 0.25x plus 0.25x squared. Okay. And so you get a quadratic that doesn't solve the problem, but is in some sense, in the least squares sense, is the best possible answer. Okay, that's it for today. Sorry to keep you over.